All right, this is the first lesson for the week, April 20 through 27. Lesson 1, it's going to be 13.4, talking about evaporation and vapor pressure. We're talking about condensed states of matter. And one of the things we've talked about is the fact that solids and liquids are condensed states of matter. And that's because the intermolecular forces between them are strong enough to hold those molecules together. And that really comes down to two factors. How big is the molecule? Because big molecules move slower at the same temperature where a smaller molecule would move faster. And secondly, what are the intermolecular forces? Something like water has very strong intermolecular forces called hydrogen bonds. And as such, water, even though it's a very tiny molecule, is a liquid all the way up until 100 degrees Celsius, where something like methane is almost the same size molecule, has non-polar bonds, so it has London dispersion forces, and as a result, it will be a gas, will be a liquid. You have to get it down several hundred degrees below zero. But what we want to talk about today is what actually happens when we get to the place where we switch from a liquid to a gas. And that is called either vaporization. Whoops, pen's bad. That is called either vaporization, which you would know as boiling, or there's another way that can happen, and that is called evaporation. They are similar to each other, but there are differences. If I have a glass of water, this water, if I set it out in the sun, especially in the summertime, very quickly the water will evaporate. And you can hear the word vapor in there. If I take and I put a piece of plastic wrap over the top, and I pull that down so that now I have plastic wrap on there, and I let this set for a period of time. Most of you know exactly what's going to happen. The water will not evaporate away. The water will turn into vapor. Eventually you'll have condensation on the top, maybe on the sides, and water then will start going back down in. So the question is, what causes vaporization? What causes evaporation? Well, let me talk about evaporation first. We'll get to vaporization later. But if I have water molecules, those water molecules, if we think of them as a whole bunch of molecules that are moving around, and I'm not going to put tons of these on. I shouldn't have made this nearly this big. These molecules are moving back and forth, and there's always a connection between the molecules. There's intermolecular forces. But every once in a while, you will get one of these. Remember that temperature is the average kinetic energy, which means if you have an average, there will be times where you'll have higher kinetic energies and times where there will be lower kinetic energies. An average means there's some that are above and some below the average. We have an average GPA in your class. Your GPA may be above that or below that. Every once in a while, what will happen is you will get a molecule that is moving very, very fast. And when that happens, it breaks free of these bonds. And then that molecule becomes a vapor molecule. So evaporation takes place when the higher energy molecules break free from the surface or from the other molecules. It doesn't help if that molecule is moving real fast down here. It has to make its way up toward the surface. And then if this is a really fast molecule, it can break free. If this was a slower molecule, it's going to hit here and it's going to come back down. This reminds me of the Red Rover, where you have people who are holding hands together. If I remember right, you're holding hands with somebody else and the people run across and try and hit it. The person who has more kinetic energy breaks through and is free. And that's what is taking place here. So there's going to be some questions in your book about what happens on the molecular level when water evaporates, and essentially it is the molecules are the fast molecules, the above average kinetic energy molecules are able to break free. By the way, kind of an interesting thing, and that is if this is an above average molecule and it breaks free, that means this the temperature here lowers. It lowers the kinetic energy. In other words, if I take if I was to take anybody and I said, okay, we're going to look at what the average height in our class is, and then I said, okay, everybody who's taller than the average needs to leave, well, then my average height is going to drop. If we take the high kinetic energy molecules out, that lowers the kinetic energy, that lowers the temperature. And that explains why evaporation does lower the temperature. The reason that we sweat is so that we'll have water on our skin, which evaporates away, and as it does that, it lowers the temperature. You gals may have worked with lacquer thinner, which is basically nail polish remover. Yeah, if you go to your medicine cabinet, if you have acetone, well, acetone would be out in the garage. If you have acetone or paint nail polish remover, and you just put a little bit on your skin will actually get very, very cold because those evaporate very, very, very quickly. Now, if I was to put a lid on top of here, we would start to get molecules that would move around in here. And as a result, we would develop a vapor pressure inside of here. And that vapor pressure would eventually reach a point where there was so much vapor in here that we would say that it was saturated, and then blobs of water would start to fall back in. So what we have is a process where molecules would be leaving, recombining, falling back in, and more molecules would leave, and that causes something called equilibrium. Equilibrium is the idea of balance, and in this case, our equilibrium would be called a dynamic equilibrium. It's dynamic because it is constantly changing. In other words, when we finally get to the point of balance, it doesn't mean there's no change taking place, but it means that for every molecule that leaves, another molecule goes back in. I think of dynamic equilibrium something like this. Imagine that you were taking a photo from above a stadium and you looked at all the people in the stadium. At any given time, let's say you have 50,000 people in that stadium watching a football game. And then some of the people go to the bathroom, but other people come back. And if you were to take a whole bunch of snapshots over a period of, say, an hour, every minute you took another snapshot, so you had 60 snapshots. If you were to look at that, you would probably, if you looked closely, very rarely would that picture not change from minute to minute. There's always somebody getting up, always somebody sitting down, always somebody going to the bathroom, always somebody coming back, somebody going out to get a hot dog, somebody coming back with food. There's constant change, but no net change. And that's what dynamic equilibrium is. And when we have dynamic equilibrium, you would have water down here, vapor up here, and roughly a constant amount of both. So dynamic equilibrium means a constant change, but no net change. All right. Now, there is an important word that I want to introduce to you, and that is the word volatile. Volatile, when we're talking about a liquid, means that it has high vapor pressure. Every liquid will put off vapor. Every liquid will evaporate, but some will do it much faster than others. The example I gave of lacquer thinner or acetone, those have a very high vapor pressure. They are then considered to be very volatile. Water has a low vapor pressure. water is not considered to be particularly volatile. And there's a whole different range of volatilities. And they're usually measured by the vapor pressure. Now, let me explain how you find vapor pressure. What you do is you take a tube that has a mercury in it, and you put that into a container of mercury. So it's in mercury. It's in some sort of a bowl. There's mercury in here. So this is filled with mercury, and you take that tube and you put the mercury in it and put another liquid inside of there and put it up in here. And what will happen is you'll have a liquid of some sort up in here. This is all filled with mercury. And then this will start to vaporize. And in fact, it'll turn into entire vapor and it'll push the mercury down. And however far it pushes that mercury down, it represents a pressure, because that's how we measure pressures, with how many inches of mercury it can support. They'll have a picture of that in your book. Something like water, just to give you a feel, water has a vapor pressure of 2.4 kilopascals at 25 degrees Celsius. We always want to measure it at a particular point or a particular amount. Something like, let me just give some examples of things that would have different vapor pressures. Acetone has a vapor pressure of 30 kilopascals. In other words, it's about 15 times greater. It would put out 15 times as much vapor. We would consider it then to be very volatile. Something like isopropyl alcohol. So this is rubbing alcohol. Would have a vapor pressure of about 6 kilopascals, or about 2.5 times what water is. And what you're going to be asked to do is try to judge what the vapor pressure of a molecule would be. Now, I know you might say, well, wait a minute, how am I supposed to do that? Well, I'm going to tell you how. It's actually not that difficult. We're not going to actually be able to guess at what this is, but we're going to be able to guess at which one has the higher or the lower vapor pressure. And basically, it comes down to the same thing that we looked at before. The size of the molecule and the type of intermolecular force. The bigger the molecule, the slower they are going to be moving, and the harder it is for them to break free. So if we have the same type of intermolecular force, the size of the molecule makes the difference. So let me give you an example. If I had methanol, which is CH3OH, ethanol, which is C2H6OH, and isopropyl alcohol, which is C3H, this would be 5 actually, C3H7OH, these have all the exact same type of bond. They all have a hydrogen bond, which is the strongest bond. But if I look at the size of the molecule, so these have the same bond, but if I look at the size of the molecule, this one is 1228, has a mass of 32. This is 2430. No, this is 12. 16 is 28. Yes, so 24, 34, 46. And this one would be 36, 52, 60. All right. Well, we would then expect this one, because it's the largest molecule, to have the lowest vapor pressure. And in fact, it does. This one has a vapor pressure of 6 kilopascals. This one is about 9. And this one is about 19. And so those are in kilopascals. The type of intermolecular force matters as well. If you were to take, for instance, a water, which has a 2.4 kilopascal, but you took methane, which has almost the same size, this is 18 and this is 16, you're going to find out that this one here has essentially an infinite, well, I shouldn't say it's infinite, but it is a vapor at room temperature. It's already a vapor. So this is greater than 100 kilopascals. Greater than 100. Why? Because this is a polar molecule and this is a nonpolar molecule. So you're going to be asked to make considerations. First thing, we're going to look at the size of the molecule. If the molecule is larger, the vapor pressure will be lower, assuming it's the same type of bond. On the type of molecule, the stronger the intermolecular force, same thing, the lower the vapor pressure. The vapor pressure will be lower. We're not going to ask you, I'm not going to ask you to do anything other than that. We're not going to have you have things that are mixed, where you have two different types of bonds and two different size molecules. We're not going to do that. So this lesson, what you should do is read 13.4, and then we are going to do the problems on this. Well, I don't know if I have it there. Yeah, we're going to do problem 32 and then 35 through 37 at the end of the book. So, yeah. If not, I will correct that on the instructions, but that should be that. So.